Okay, so thanks for coming. So you heard from Neil about a pulsar timing array. I'm going to talk about a metronome timing array, which is a demonstration using two metronomes and a microphone to simulate the workings of a real pulsar timing array. Now, this is work that I've done with several collaborators as part of the Nanograv collaboration. Um, Python routines, so code and sample data, are available under the Les link that you have already. So if you go to the Les GitHub page that I have, and you go down to the PTA demo part, you'll be able to access the code and some sample data that I'll show you. And also there's a draft of a paper that's currently under review by the American Journal of Physics with all of the details. Okay, so you can take a look there if you want. Okay, so the purpose of the demo is basically to illustrate how a pulsar timing array is used to search for gravitational waves in the context of a much simpler model using metronomes and microphones. Okay, and in the process, we'll introduce concepts and techniques that are actually used by real pulsar astronomers when they do their analyses. These concepts include some of the things that Neil talked about yesterday and some things that he also talked about today. So the first technique or concept is this idea of folding. When you have periodic data, you can fold the data to determine the period of the pulses, and you can also use the folding to calculate pulse profiles, which are then used to determine measured time of arrivals. Another concept is what's called detrending. If you look at the timing residuals and there's a strong linear trend, then that's evidence that your pulse period is not accurately determined. So if you remove that linear trend, you get an improved estimate of the pulse period, which then helps you with your timing model. We also need to use match filtering for calculating measured times of arrivals of the pulses. We have to we have to use or assume some sort of timing model. Nothing as sophisticated as what Neil talked about yesterday, but we need to assume some simple timing model in order to determine when the expected times of arrivals are. And then at the end, we'll need to do correlation analyses, basically to extract the common quote-unquote gravitational wave component of the signal in the data. Okay. Now, I should say that the purpose of doing this demo is to use it for education and public outreach talks to the general public, or also we're considering the possibility of using it for an instructional undergraduate laboratory. Okay, so let me just start. So here's roughly how the demo goes. I'll sort of first explain what we do in general, and then I'll show you how it's supposed to work on sample data, and then we will do it live and see what happens. Okay, so basically here's a pulsar. Okay, here's a pulsar somewhere in the sky over here. Okay, and then here's another pulsar, different frequency, somewhere else in the sky. Okay, and I don't have a USB microphone, so I typically use the internal laptop microphone on my laptop here. Excuse me. Oh, that's okay right now. I don't need to. I don't need to project right now. But anyway, so you've got these two metronomes, basically representing two pulsars ticking, at different locations in the sky with different frequencies, etc. We've got the microphone here representing a radio receiver on Earth. And then what I do is I move the laptop around, okay, to simulate the effect of a gravitational wave. Okay, so there's no real wave, but by moving the laptop around, I'm changing the time of arrivals of the pulses, because sometimes I'm a little bit closer to that metronome, sometimes a little bit farther away from the other metronome, etc. And because this is a common effect, the disturbance in the arrival times will be correlated across the different microphone metronome baselines. So this motion here of the microphone is sort of like the earth term that Neil was talking about. Okay, so there is no pulsar term that I'm worrying about, that I have to worry about. I'm not going to move the metronomes. I'm only going to move the microphone here with my laptop, and the effect that I see should be correlated. So when I determine timing residuals, I should see correlations in those timing residuals. Okay, yes, yes. Okay. Okay, so that's the basic idea, okay? And what we should find is that the correlation that we determine should depend on the angle between the microphone metronome baselines in a very specific way for this particular problem. And it won't be quadrupolar. It will actually be dipolar, okay? So here's what the data would look like. So this is some sample data that I recorded a couple months ago. It consists of pulses from 2 metronomes, okay, taken for 8 seconds, okay, and I was moving the microphone around. And the question that we need to ask is there evidence of a gravitational wave in the data? Is there evidence of this common microphone motion? Okay, that's the question we need to answer. Now, we can sort of unpack that question a little bit more, okay? So is there a common disturbance to the pulse arrival times, which we'll call TOAs? And if so, is this disturbance correlated across the different metronomes as expected for a gravitational wave? So we're going to have an expected correlation, which we'll compute sort of analytically, and then we'll compare that to the measured correlation for different angular separations. Okay, now to unpack things further, to talk about a disturbance means a difference between some measured quantity and some expected quantity. So a disturbance is actually a timing residual, which is the difference between the measured arrival times of the pulses and the expected time of arrivals. To say that that disturbance is common means that there should be a correlation between the timing residuals. And the way that I'll determine the correlation is basically calculate this coherence here. So x1 and x2 represent 2 timing residuals. So I'm going to form a correlation, which is really nothing more than a time average product of the 2 timing residuals, and then divide here. So this is a normalization that puts this between -1 and 1. How do I determine the measured TOAs that come here? Well, basically, I'm going to take the recorded data and correlate that with a pulse profile, sort of shifted in time. And this correlation, as a function of the time shift, will have a peak at the arrival time of the pulse, or pulses. What about the expected TOAs that go in there? Well, I get that from a timing model, which in this case is very simple. It's basically just equal spacing arrival times, equally spaced by the period of the pulses relative to some reference pulse. Okay, so this is the time of arrival of some reference pulse here, and then we just take equally spaced times as the expected arrival times. Okay. Now, to calculate the measured TOAs, we have to do match filtering. To do match filtering, we need a pulse profile. We also need a period for the expected arrival time, so we have to get those. We get those by folding and detrending single metronome data. So there's going to be sort of 2 parts to this demonstration. One, when I have the metronomes just running individually, and then the second part will be when I've got 2 metronomes going at the same time and I'm actually moving the microphone. Okay, And then finally, to calculate the expected gravitational wave correlation as a function of the angular separation between the two metronomes, we need to use an expression for the timing residual response, which is really nothing more than the change in the nominal change in the distance to the metronome when I move the microphone, which you can get by just taking the unit vector in the direction of the microphone, dotting that into the position of the microphone. So this is really like a Romer delay term. Okay, and if you take that as your timing residual response for metronome I, where I is 1 or 2, you can calculate the correlation coefficient here, and you should find a cosine of the angle between them as the expected correlation. And if you did the exercises that I gave you for the stochastic background search, this was something that I asked you to do in the context of electric dipole antennas. Okay? Okay. Any questions so far? Is it fairly clear what needs to be done? Okay. So there are two parts of the analysis. One is the single metronome analysis, okay, which whose purpose is to produce the pulse profile and the period that I then use for the double metronome analysis. So I'm going to need to fold the data. Once I have the profile and the period, I can use the period, well, I can use the profile to do matched filtering to determine the measured time of arrivals, okay? I use those measured time of arrivals or the arrival time of one pulse, which I'll take as my reference time of arrival, take the period, put it into my timing model to get expected TOAs. So I'll have a set of measured and expected TOAs. I could then subtract those two to get the residuals, and I look at the residuals and see if they're if there's a linear trend or not. If there's a linear trend, I remove that to get an improved estimate of the period. So the single metronome analysis is basically to get a period and a pulse profile. Then I used the periods and the pulse profiles that I get for the two metronomes to do the double metronome analysis, where I've got the microphone moving. Okay, so I've got the double metronome data. I do matched filtering using the profile from metronome 1 to get the measured time of arrivals from metronome number 1. I use the period that I have from metronome number 1 and the timing model to get the expected TOAs. I subtract to get the residuals. I do the same thing for metronome number 2, and then I correlate, and I get my measured correlation coefficient that way. And then I compare that measured correlation coefficient with theory, which, as I mentioned before, predicts a correlation coefficient that goes as the cosine of the angle between them. And then the question is, do those two things agree? Okay? And for some sample data that you can download, if you do this, what you find here is that for 5 different angular separations, 0, 45, 90, 135, and 180 degrees, the measured correlations are these orange dots here with some error bars, and then the blue curve is the expected. Okay? Now, this doesn't look like Hellings and Downs, okay, because Hellings and Downs is quadrupolar. Okay, this isn't real gravitational waves, but nonetheless, the purpose here is to illustrate that there are correlations, and that if we measure those correlations, they should match up with what we expect. Okay. So this is the smoking gun signature, to use Neil's words, for the metronome demo case. Okay, so here, just to show you, we wrote 2 graphical user interfaces to do these calculations. This is what we'll do live in just a minute, but basically for the single metronome analyses, you can record the pulses from the 2 different metronomes, which are displayed here. You can play them back and sort of listen to them and plot them. You can calculate the pulse profile and the pulse period by folding the data. Here's what the pulse profiles look like. Okay, they're very complicated things, actually, if you look in detail. And then you can calculate the residuals and detrend the residuals if necessary. And what you find here is that the residuals are actually at the microsecond level. So very small, which means that you can determine changes between the changes in distance between the microphone and the metronome of order millimeters. Yes.
Joe, so how, from pulse to pulse,
Yes.
how consistent are these profiles on the metronomes?
They're
Is that a stacked?
yes. This is a folded profile.
Okay.
So I don't have to stack for individual. I don't have this extra layer of stacking or folding that Neil talked about last time. I fold the data to get one profile, which I then use as a template to determine the time of arrivals.
If I took the difference between that template and any one
Yes.
pulse,
Mm-hmm. How
in
different?
terms of like, just
Right.
residual,
Right.
I'm just curious how sort of, in terms of the metronome
Mm-hmm.
manufacturing,
Yes.
how uniform a click is it making every time?
I can't give you a quantitative answer of that.
Interesting. Though.
Okay. Yes, it would be interesting to look at that. Mm-hmm.
I'm just thinking about this as you talk about it with respect to pulsars. So when you do this measurements with a pulsar antenna, you're to some extent pointing.
Yes.
So do you have an effect here that the microphone has some directionality in it?
Yes, yeah. So there are complications here because we're dealing with sound. You've got reflections, and it's so that's why I'm a little nervous about doing this live, because it works sometimes and it doesn't work so well other times. But we'll see. So that's why I'm showing you how it should work first. Okay. So this is the single metronome analysis. Okay, whose main purpose is to produce these two profiles in these two periods. Okay. And then we do the double metronome analysis. So here's some sample data for an analysis where the two metronomes are in the same position. So the angle is 0 here. Okay. These values here correspond to sinusoidal fits to the data. Okay. So actually, I'm not going to move the microphone around in a random way. I'm going to move it around in a circle, uniform circular motion, for reasons that I can come back to later, okay? And actually that will mimic an isotropic, unpolarized gravitational wave background, okay? So I move it in a circle, and the amplitude of the motion is large enough that the residuals should have a very obvious sinusoidal behavior. I then fit a sinusoid to the data, and then I correlate the best fit sinusoids in order to get the correlation coefficient, which for this case here gives 0.98, which is close to cosine of 0 or 1. Okay, then I do it for 45 degrees, and I got something like 0.77. I do it for 90 degrees, I got minus 0.27. I should have got something closer to 0. Okay, you should see these curves just shifting relative to one another.
Joe, each time you do this,
Yes.
you have to try and reproduce.
Yes.
Circular motion.
Yeah. So it's
You should have Martin build a turntable with a receiver.
that's right. Yeah. So right now you can think of this as being in the prototype stage. I mean, the theory, I understand sort of theoretically how it works, and but the experimental setup is not.
I mean, the circular motion is only because that gives you a simple model. Right?
It gives me a simple model that I've got a sinusoid here, but it mimics exactly an isotropic, unpolarized gravitational wave background. I could also just go like this, but that would be polarized. There would be linear polarization, okay, associated with that. Okay. You do it again for other angles, 135 and 180, or whatever angles you want to choose. You look at the correlation, so minus 0.72 for 135, minus 0.99 for 180 degrees, and then you plot and compare. Okay? So now we will try to do this live. Okay, so here we go.
You sacrificed to the demo gods.
No, I didn't. So, okay, so let's try this now. Okay. Okay, so you know how it works. There's nothing sort of, I'm not going to be doing anything new here except trying to reproduce it live. Okay? Yes, it. Okay. Okay, so let's. Oh, and I should point out the following. Can you hear a difference between this? Oh, and that? Okay, so there are two modes, and actually that's nice because it makes the profiles more distinct. So not only are the beats per minute different, but the shapes of the profiles will be different as well. Okay, so I'll take metronome number 1 here. It's beating 208 times per minute. It's in mode mode A. Okay. So I'm just going to sit here, or maybe sit here. Okay, and I've got it all set up. Where is it? So I'm going to call these things, change the name. Okay, so that's going to be the name of the data. Okay, so quiet on the set. We're going to record the pulses now. So I'm going to click here. Okay, so we're done recording. You can see in the sort of the left-hand side. Okay, so now I'm going to stop this. Okay, and now I'm going to play back the pulses. Okay, so you should hear what you just heard. Oh, you can hear some noise in the background. So we'll see if that loud click. Okay, so there are the pulses. You could see the right here. Okay, let's try to go with it and see what happens. Okay, so we'll calculate the profile here, which is basically just folding the data. So it's trying different segment durations, and then it basically divides the data up into those into segments of that chosen duration, and then averages things up, and it looks for sort of a maximum. And when it gets maximum output, then that's the correct period. Okay, so that's what we get for the folded profile.
Why didn't you just like
Fourier transform.
to
I tried Fourier transform, but that didn't seem to work as well. Okay, I don't know. I mean, it's folding seems to work fairly well. So let me try this next one. Okay, so this is 184 in the second mode. Okay, so let's try that. Okay, quiet on the set here. Okay, so I'll play those back. Okay, there they are. Calculate the profile again. So it's trying different periods, trying to get some maximum in the averaged output. And when it does that, that's the period that it thinks the pulses are coming at. Those values now, here this 0.3261 is what you get if you just take the nominal 184 beats per minute. Okay, so that's the profile for that. Now what I'm going to do is I'm going to use that. I don't know if I maximize. I maximize something. Okay. I don't know if it's the maximum amplitude or some of the squares just to get the period. Okay. It seems to work. So now I'm going to use those profiles, do matched filtering against those pulses here to determine the. You can see it's calculating over there. If this says bad, that's bad. That's a bad sign. But because there's no microphone motion, the residuals should be pretty good. Um, that, that's right. Okay. But look here. Look at how linear these residuals are. Okay. And that's because this period that was determined by the initial folding isn't quite right. Okay. So if I remove that trend, so I'm going to remove the linear trend, watch how this number changes. So it's 288561. So now it's 567. And you see now that I have residuals that go between -1 and 1 microsecond. Okay? Now I'm going to do the same thing here for metronome number 2. Calculate the residuals. And you can see it's calculating over there.
So it's split the data up into each pulse there, and it looks for the residual for each pulse.
Well, what it's doing is that when you do the matched filtering, you get a correlation function that has these local maxima at the measured time of arrivals. And then what I do is I take the pulse that has the largest correlation as my reference pulse, and then from there I go either forwards or backwards multiples of the pulse period as my expected time of arrivals.
Pick out the maximum within those. Do you do like a window there? You just pick
Oh, yes, I have to do a window to get the because there's several local maxima. Okay, so again, a linear trend, detrend it, and you see again around a microsecond. Okay, so that looks pretty good. Okay, so let's. Where's the glitch? Oh, okay. Okay, so let's see. Let's cross our fingers and this one here.
7.5 seconds.
Okay, okay. Let's ignore that. Okay, so let's see what happens. So I'm going to close this. So we're done. The single metronome pulse analysis did what it needed to do. Okay, and now we're going to run the second one. Okay, and I'm going to turn both of these on. Okay, so now both are going at the same time. Okay, so let me just. So I've got to first change the name of the data files. So I'm going to keep this 0 here for 0 degree separation. The profiles have the name T for test. Okay. Oh, I forgot to record what these were, but hopefully they're not too far off. That could be a problem. Okay. So I'm going to load the pulse profiles. There they are. Okay. So now I'm going to record the pulses. So this is the complicated thing. So it requires a lot of skill here. Okay. So I'm going to hit the record button, and then I'm just going to move it around in a circle like this. It takes 8 seconds of data. So here I go. Okay, finished recording data. So now I'm going to play back the pulses. And hopefully I chose the amplitudes, the volumes, similar enough that they're not way off. Okay, so that's the data there. Okay, you can see that sometimes the pulses line up, but that shouldn't be a problem for matched filtering. Okay, so I'm going to calculate the residuals, and I'm just going to move this over a little bit so I can see if I'm. Yes.
When you load I guess you have to load the pulse profiles.
Yes, I did. Yeah.
I suppose in future, if you had it load the pulse periods, and then you wouldn't have to remember.
That's right. That's right. Good idea. Okay. Okay. Yes. Okay. So let me calculate the residuals here. So it's calculating the residuals. Hopefully it'll look somewhat like a sine wave. There are about 24, 28 residuals. I can't remember, depending on what the beats per minute are for.
So Joe, does the match filter pick out metronome 1 well enough for metronome 2 that you don't get additional peaks from metronome 2 somehow interfering with metronome
Yeah,
competing with metronome 1's
yeah,
filter?
yeah. So there it is.
So yeah, to Bruce's point, Joe, if you took profile 1 and profile 2 there,
And swapped them.
no, and calculated their match,
Yeah.
it would be interesting to see what their match is. It must be fairly low.
Okay. So there it is. You see that they're pretty good sine waves. Fit sinusoids. Ooh. Okay. So okay. No. This is good. This is good. Okay. So let's see. So what I need to do is I just need to choose a better value for my amplitude here. Yeah, so my initial estimate, maybe if I choose this to be 200, and then I fit sinusoids. Okay, that's better. Okay, so my initial estimate was too far off. My initial estimates are chosen based on past experience for doing this. Okay?
So Joe, let me just ask a question. So sound travels at 300 meters per second.
Yes.
And so that means that in the thousandths of a second, in a millisecond,
Yes.
it travels 3/10 of a meter, which is 30 centimeters. And so in, let's say, 100 microseconds, that's a tenth of that. That corresponds to about 3 centimeters of motion.
That's right. So I'm moving.
According to your laptop, that was about a 3 centimeter.
Yeah. So I do it about like 5 centimeters, and that corresponds to about 10. It corresponds to about 10 to minus 4 seconds, which is much larger than the microsecond precision.
Right, it's 100 microseconds.
Okay.
It's about the amplitude of your
Okay.
sinusoid.
Okay. So this is good. Okay. So one is good. Okay. So let's try now over here. So I'm going to put these at 180 degrees. Okay, so I sit down here. Okay, and you have to, right, you don't want to do it like this. What for what? Oh, oh, no, wait, no. Well, you can write it down. Okay, yeah, if you want to write there. 0.97 is close. Well, we're only going to do a couple angles. Okay, so here we go. I'm going to try it again here. So okay. Oh shoot. Yeah. Okay. Yeah, that's right. So I made a mistake. I should have changed that to 180, but that's okay. I don't need to worry about that. But typically you can change the name of the files. Yeah. So this is more a test of how well I can move things in a circle. So let me calculate the residuals again while I turn these things off. Oh, that's not as nice a sine wave. But this is again the problem with my motion here. Okay, so there are bugs that can be worked out or should be worked out in order to have this. Let's see what happens here. That's not bad.
Can I ask a question? If you move your laptop left and right, or forward and back,
That's linear polarization.
would you get the same pattern?
I don't think so, because you can then, right? So if I do this, then that really shouldn't change the arrival time, because it's not moving toward or away from the metronome. So I'm That's right. But then I'll be, yeah, yeah. I mean, you can move the microphone around in any way whatsoever. But in order to get the nice cosine zeta dependence, it comes out very simply for the uniform circular motion case.
But in fact, of the uniform circular motion, you're actually insensitive. In the case now of the separated microphone,
Yes,
you're insensitive to motion either in the horizontal or vertical direction. You're only sensitive to motion along
that's
the
right.
longitudinal
Yeah,
scale.
yeah. And so the calculations or the expression that I wrote for the timing residual is is ignoring any curvature of wavefronts and things like that. Okay, so this worked fairly well. Okay, -9 -0.97. Okay, let's see this. The 90-degree case is always the hardest one. Okay, so let's try that. Okay, so 0 and 180 are fine. Yes, I'll rename it. Okay. Okay, so the problem, right, is you don't want, since the microphone is here, if you put this sort of thing up here, you're getting, right, anyway, okay, so we'll try and see what happens. So I have to hold it sort of in this funny way. Yes, we have to.
Yeah, you buy a microphone and move it around.
Okay, so here we go. Okay. So like I said, this is usually problematic because of not holding the laptop properly. Okay, let's calculate the residuals. So the residuals usually for the first metronome are nice because it's sort of kept in that same location, whereas the residuals for the second metronome usually are worse when I put it at angles like this. So again, a nice sinusoid there. Well, wait, no, it's not yet. I gotta. So the last one was 180 degrees out of phase. So we'll see what we get. We'll see. So we're going to fit sinusoids. It's 0.2, not perfect, but it's usually as good as I can do. Maybe we'll do one more and then we'll stop because yeah, should have been 0. Okay, but anyway, I mean, if I did it again, I might get something closer. I might get something a little bit away. Yes. So okay. So how did I get those error bars? Well, so those were calculated using the uncertainties and the best fit sinusoids. And my sinusoid is not necessarily. Okay. So let's try this.
So is that just a standard Python least squares
Yes. Yeah. Yeah.
called up?
That's right. Yeah. So all of this is Python. You're more than welcome to modify the code, improve it, send me suggestions about how to make this better. Let's just try this last bit here. Okay, so this will be, say, for 45 degrees. Again, you see the precision with which I measured the degree. Just very, very rough. Okay, so let's try this. Okay, calculate residuals. Okay, so that's the basic idea, right? So we use the single metronome analysis to get the profiles and the periods. Then you have the double metronome analysis where you move the microphone around. You do the cross correlation and see if you get agreement or, fairly close agreement with the cosine zeta dependence. And you can do it for different angles. You can do it for different types of motion to see what happens. Bruce had suggested moving have somebody move the metronomes around to simulate the effect of the gravitational wave in the vicinity of the pulsar. But if that's done incoherently, it shouldn't change things. Okay, so here the residuals are done.
So you just need to generalize this to 4 or 5 metronomes and you get all the angles at once, and all the different combination of angles.
Okay. Yeah. So again, this is not as good as I would have liked, but the basic idea, hopefully, I illustrated with the sort of examples that I showed. Okay. So I'll stop there. If you've got questions, please let me know. And like I said, any suggestions or ways to improve this would be great. A graduate student at UTRGV actually wrote a smartphone implementation of this for Androids where you can use the smartphone either in metronome mode or microphone mode. That's a little bit behind as far as its capabilities compared to the Python code. If somebody wants to write an iPhone implementation of it, you're more than welcome to do that. So, questions? Yes.
For PTAs, you assume always that the pulsar, that you have plane waves, radiation waves.
Not always. I think there are some cases where the pulsar is sufficiently close and you know the distance that people actually include the effects of the curvature of the waveform, right? Or I've seen that in. Excuse me. Oh, I'm sorry.
So if
Okay.
the source is closer than the pulsar, you would.
No, it won't be so close than the pulsar because we're talking about black holes. But I had that in some of my expressions. There's the first correction to the spherical wave fronts, and for some black holes it might be an issue, but it's a small effect, pretty much. I mean, they're pretty much plane waves. Actually, there was a paper by Sam Finn,
Yeah.
Ding and Finn, that looked into that, but it's a pretty minor effect. It's
Mhm.
because the black holes are going to be megaparsecs away, and the pulsars are kiloparsecs away, and so you've got factors of thousands. Well, there's the wavelength actually comes into the gravitational wave as well. So it's just not a significant effect.
So I just checked it as you were doing this. So if you do this in a lab, you can buy an old, you can still buy on Amazon a cheap turntable
Mhm.
and a Bluetooth microphone.
Okay.
Just
Yeah, you need a Bluetooth microphone, otherwise the cable's going to get all wrapped around.
Okay. Bluetooth microphone. Okay.
$30
Great.
each.
Yeah.
Okay.
And
What if you just have a microphone on a cord and you
You
just
can do a pendulum.
Yeah. I mean, I did buy those like karaoke microphones and had that, but these pulses were very ugly then because there was like a band of noise associated with this. Where this particular laptop microphone has ambient noise reduction, so the pulses are much cleaner.
Somebody suggested something, which is hang your microphone from a string.
Yes.
That's very nice because that will give you, always the same period with the decaying amplitudes. You'll see that nicely.
Right. So something like this, and you can have it go around in a little
Yeah,
circle.
these Bluetooth mics that are meant for speaking,
Yes.
they should be pretty good.
Right.
Okay.
The ambient noise cancellation thing.
Are they fairly directional or omnidirectional?
I don't know the answer.
Okay.
I would
Okay.
probably pretty on.
Okay.
I mean, you could even plug in a headphone like this to the laptop that has a speaker on it. And
Okay.
around.
Okay. Yep. I should try that. Okay. Thank you.
You're having way too much fun, Bill.
Yes, I know.